Okay, welcome to part 2. So we'd finished going through these numbers and deciding what sets they belong to. Now it's also possible to describe all of this in a Venn diagram. Okay, I'm just going to show you how that is done. Okay, what we've got here is got the universal set is all numbers that could possibly exist. And actually what I've just shown you is there are some numbers that are not real. Okay, so if I make this circle the set of all real numbers, this set here, then there are some numbers that could go outside that. For example, the square root of -2, not a real number. 6/0, not a real number. Okay, now within the real set of numbers, we got all rational numbers. All rational numbers are real numbers. Okay? In that set, we've got all integers. Okay, because all integers are rational. And within that, we've got natural numbers. Okay, because all natural numbers are integers. So natural numbers is a subset of integers. And natural numbers is a subset of rational numbers and real numbers. We could describe rational numbers as a subset of real numbers. Okay, and we could fit each of these numbers into the Venn diagram. You know, for example, root 16, that's all of them. So root 16 goes there, as well as 19. Okay, -2/3 is rational, but it's not an integer or a natural number. So -2/3. If I pick 2π, well, 2π is irrational, but it's still real. So 2π would fit in there. Okay, I hope that's making sense. I hope you understand the idea of a subset. Okay, let's move on. So, with that knowledge in mind, stop your video and have a go at doing this. But just note that this time we're saying the universal set is all real numbers. So, for the purposes of this question, there's nothing that is not real. So, the universal set is the real numbers. So, start off there. Okay? Right, stop the video and have a go. Okay, I hope you did that. So we've already said where the real number set should go. Then we've got, inside that, we've got rational numbers. Inside that, we've got integers. Inside that, we've got natural numbers. Okay? So place these numbers in the correct place in the Venn diagram. So half is rational, but it's not an integer or a natural number. So half goes here. Root 2 is irrational, but it is real, so it's going to go here. Okay. 0.3 recurring. That is a rational number because it repeats itself. It has a pattern. Okay, it's a rational number. It's not an integer or a natural number, so that's going to go in here. 0.3 recurring. -5 is an integer but not a natural number, so that's going to go here. 5 1/4 is a rational number, but it's not an integer or a natural number. 0, got to be really, really careful with this one. 0 actually goes here because it's both an integer and a natural number. Okay, it's not a positive integer, but it is an integer. Okay. And 10, well, that will go inside because that's natural, an integer, and rational, and real. Okay? What about this one here? 0.213700561, a number which does not terminate or recur. So it goes on forever and ever and ever with no pattern. So it's a real number, but it's not rational. 0.213700561 goes in that set there. Okay? Right, let's have a look at these statements. The natural numbers are a subset of the integers. We can see that is true because this circle is entirely inside this circle. So that's true. Okay, the integers are a subset of the rational numbers. That's also true for the same reasons. The natural numbers are a subset of the rational numbers. Again, this circle fits entirely inside this circle. So all natural numbers are part of the rational number set. So that's also true. All three of them were true. Okay? And finally, shade the region representing the set of irrationals. Well, hopefully you can see this green coloured set is where all the irrational numbers have to go. Okay, so it would be in there. Okay, I hope it's making sense. If not, just get help. Okay, it's not a problem. Okay, now, I said that as long as a decimal number repeats itself or terminates, or it finishes, then it's a rational number, so it can be expressed as a fraction. So let's just have a look at this one. We've got 0.77777, that's a 0.7 recurring. Okay, that is a rational number, which means it can be expressed as a fraction. Okay, so what I'm going to show you now is how to express this number as a fraction. So what I'm going to do is I'm going to use a bit of algebra. I'm going to say x is equal to 0.77777. Just write a few examples of it and then dot, 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 dot. What I'm going to do is I'm going to then multiply both sides of that equation by 10. So I'm going to get 10x equals 7.7777. Okay, so I'm going to call this equation 1 and this equation 2. And all I'm going to do now, just like when we solve simultaneous equations, I'm going to do equation 2 minus equation 1. So if I do that, left-hand side, I will get 9x, because 10x minus an x is 9x. And on the right-hand side, we've got 7.7777 minus 0.7777. You can see what will happen is the decimal bit will cancel away, and I will just be left with 7. So now solve for x. X is equal to 7 over 9. Okay, so 0.7 recurring is 7 over 9. It can be expressed as a fraction, therefore it is a rational number. Okay, let's just do some more examples. Just delete. Okay, 0.41 recurring. Now you've got to be careful here. So 0.41 recurring is the same as 0.414141. So again, let that be equal to x. Now, am I going to multiply that by 10? No. Actually, what I'm going to do this time is I'm going to multiply both sides of the equation by 100. So 100x is equal to 41.14141414. And the reason is I need this decimal bit. Sorry, I've done it wrong. Sorry, just bear with me. Wrote that wrong. 41.41414141. That's better. Okay, I need the two decimal bits to be the same so that when I do my subtraction, they will just disappear. Okay, so again, I'm going to do equation 2 minus equation 1. I'll get 99x is equal to 41. So x is equal to 41 over 99. Okay, again, hoping that makes sense. If you can simplify that fraction, then you should, but I don't think that one simplifies. Right, one more example. Let's just write the answer there. So that was 41 over 99. Okay, 0.324 recurring. So that's 0.324324. Let that be equal to x. This time, you probably can tell me what's going to happen. I'm going to have to times by 1,000. So 1,000x is equal to 324.324. And do equation 2 minus equation 1. We're going to get 999x equals, this will cancel away, 324. So x is 324 over 999. Now that one does simplify. I know that both of those numbers divide by 3. I'm not going to do it. You can work that out yourself. Okay, so once you've got to a point where you've got the solution, you should then simplify it into its lowest terms. Okay, I'm just going to pick one more example actually, just try and see if I can confuse you a little bit here. Let's pick this one, 0.14 recurring, like that. Okay. Now what that means 0.14444, because the dot is only over the 4. Okay. So what I'm going to do is I'm going to let that be equal to x. And I'm going to do the same thing. I'm actually going to times by 10. So I'm going to get 10x is equal to 1.4444, like that. But now I've got a problem actually, because if I do equation 2 minus equation 1, it won't work, because I'll get 9x, that will work, but this and this, they don't cancel. Okay, they don't cancel out, so we've got a little problem there. So I have to do a little extra thing. I need a third equation, and I'm going to do 100x as well, which would be 14.4444. And now what I'm going to do is I'm going to do equation 3 minus equation 2, because that will allow me to cancel off the 0.4 recurring. Okay, so I'm going to get 100x minus 10x is 90x, is equal to 14 minus 1 is 13. So x is equal to 13 over 90. Okay, so 0.14 recurring is equal to 13 over 90. Since 13 is a prime number, we know that that won't simplify any further. Okay, I hope that makes sense. Okay, so I'm going to stop the video there and we'll do part 3.